Cool. Welcome everyone to the Cantina / Ethereum Foundation Pectra Hacker House. We are very excited to jump into things today, and we've got a big schedule. So I will not take up too much time, but obviously very excited. We've got the $2 million competition running at the moment to try to break Pectra before everything goes live. So lots to learn, and I will pass it over to Matt and Terence for an intro into Pectra now.
Oh. Hello, guys. Welcome to the Hacker House. I'm excited to talk to you guys about Pectra. Woo! All right, you can see my screen up here. I'm going to introduce the execution layer proposals that's going into Pectra, give you a little summary about what those proposals are going to do. And Terence will give an introduction on the CL side about Pectra, talk about the summary of some of those EIPs, and I think we'll take a break after that, and we'll dig into the implementations of the EIPs a bit later this afternoon. I don't know how this is going to work with a live stream, but feel free to just interrupt me if you have a question or need a clarification on anything or a comment. I'm happy to have it be a bit interactive. I don't know if the people online if there's a place for them to post questions, but I can answer those as well. Alrighty. Okay, so on the EL side, I'll just go in numeric order. We've got 2537. 2537 has been around for quite a while. This is the precompile for BLS 123D1, and it introduces quite a few different contracts. So you can see in the specification all the different addresses for the different BLS operations it's going to allow. I'm not an expert on using BLS by any means, but my understanding is this gives you enough of the functionality to do most of the things with BLS that you would hope to do. So this one has been a long time coming. Originally created in 2020. It took us a while, but it is finally going live with Pectra. All right, next up is 2935, another 2000 EIP from 2020 also. This one's gone through quite a few iterations. And the idea here is that we want to put the historical block hashes directly into the state. And there's a lot of reasons why today it's actually possible using the beacon route that's available from the 4788 contract to figure out what the historical block hashes are. But due to wanting to move to a world that's stateless, possibly with Ferkel, we also need to provide the block hashes that go into the block hash opcode. So every time you call a block hash on the EVM, the node that's executing it needs to know the last 256 block hashes. So part of the idea with 2935 is to not only have a place in the state where it's very easy to access historical block hashes, the last 8192. It's also possible for you to pipe the block hash opcode to use this contract as the backend. And if you're familiar with the Cancun upgrade, we had another EIP 4788, and 4788 and 2935 provide like very similar functionalities. 4788 is providing a contract that you can call in the EVM, and it gives you the beacon chain routes. The 2935, same idea, except instead of the beacon chain routes, it's providing the execution layer block hashes. And this is kind of part of this big suite of system layer contracts. 4788 was the first system level contract that we had. And now 2935 is another one. And we'll see with a few more of these EIPs, there's quite a few system contracts in the Pectra upgrade. This is kind of a consensus layer and execution layer change, but a bit more on the execution layer. So previously, when the consensus layer was bootstrapping, getting deposits, new validators were coming online, they would follow the receipts that were coming out of the execution client, and they would look for log events that were emitted by the execution layer contract, the deposit contract. With 6110, we have this new functionality, another system contract where, or sorry, not another system contract, but a system operation where the execution layer, after it executes the block, will actually go through the logs and look to see if any are from the deposit contract, and it will take those and bundle them up and ship it off to the consensus layer via the engine API. So this was a nice change. It sort of removed kind of a weird aspect of the Ethereum protocol where you have this ETH1 this ETH1 root voting committee on the consensus layer, and there was a very long period of time where you had to vote to figure out what that root was going to be, and then you could finally accept that as accepted and bring deposits onto the chain from that. So this is going to simplify that and sort of remove some attack vectors around accepting that root. Okay. Then we have 7002. 7002 is another kind of cross-layer execution and CL related EIP, but this one is, again, a system contract. It adds a contract that it's possible to call from EVM and initiate an exit or a withdrawal on the beacon chain. So the way that kind of works is you can think of this contract as some queue that exists in the EVM, and you submit a call into that queue and it sits there. It's not really validated. It's just you've paid a small fee to get into the queue, and then it's dequeued as part of a system operation, and the consensus layer does the validation. If the request comes from an authorized address, your execution layer address that's associated with your beacon account, it's possible for the consensus layer to then begin that withdrawal or exit depending on what you requested. And similarly, 7251, which is much more of a consensus layer change, but also has a small execution layer aspect of it. And this is, again, allowing you to kind of control that validator from the execution layer. A lot of things in Pectra are sort of focused on giving programmatic access to your validator via system contracts. And so Terrence will talk a little bit about what 7251 means on the consensus layer, but for the execution layer, it's just another system contract. If you want to take multiple validators that you have running and consolidate them to a single validator, it's possible to start making those requests directly on the execution layer. And it's possible for a smart contract to start making those requests. So these types of things are super useful for staking pools and other like programmatic staking operators. All right, 7623. There's a lot of EIPs in this fork. Okay, so this is an execution layer change, not a system contract. The idea here is that we want to increase the call data cost, but we want to do it in this way where we don't affect the typical uses of call data and are only affecting these like very specialized large use cases of call data. And the idea here is that we can actually reduce what the worst theoretical size of a block is, because right now we sort of have to design all these systems around what is the worst case of the blocks in the network. And if the block can be, 1.5, 2 megabytes, even though it's, we're never, the typical size of a block is never that big, we have to know that it's still possible, and we have to design the system to be robust when that happens. And so the idea here is that we want to reduce the maximum size and bring it much closer to what the typical workflow is for call data. And then we can kind of increase how much call data we allow on the chain, because we don't have to worry about this, 2-3x multiplier on the worst case scenarios. Okay, and 7685, this is a EIP that sort of simplifies the interaction with a lot of these system contracts. System contracts in general are creating this message bus from the execution layer to the consensus layer. And originally when all of these were proposed, they were sort of proposed independently. And we were sort of thinking, and you're going to just have in the block header a commitment to the list of all of your individual requests. And as we started implementing this, we realized this was quite brittle. We kept adding new requests. There's 3 request types in the Pectra hard fork. And so that was going to mean 3 new elements in the header, 3 new elements in the block, lots of frustrating implications of this. And so with 7685, we once and for all wanted to just come up with a standard wrapper for request objects. And it follows similarly to how transactions are encoded and committed to in the block header today. We use the EIP 2718 prefix for transactions. So 7685 introduces a prefix. Each request type, which we'll see when we do the code walkthrough, has a specific byte prefix that gets appended at the front of that request, and then it's put into the Merkle tree, hashed, and the commitment of all the requests in the block go into the header. And this gives us nice functionality in the future. If we want to add more requests, it's not going to be as painful as it was in the Pectra upgrade to sort of just introduce this facility in the first place. So that's 7685. And there's so many EIPs in this. I guess this is more of a CL. Okay, 7702. This is a really good EIP, I hear. So the idea with this is that we want to allow EOAs to have smart contract-like functionalities. Over the years, we've just generally felt that smart contract wallets are great, and we want people to use smart contract wallets more. But the reality is that the total value on pretty much any metric, whether it's value locked, volume, all of these things are kind of dominated by EOAs, and that just forces dApp developers to not give first class priority to smart contract wallets. And that's kind of why we see pretty poor UX for smart contract wallet users today on regular dApps. And so with 7702, the idea is that we want to bridge this gap. And we want to not have 2 different interfaces that dApp developers have to build for. There's just the assumption that if you are interacting with an Ethereum account, that you can submit a batch of transactions and you can do more sophisticated workflows. So that's kind of, and also gas sponsorship was a big piece of this, which is talked about a bit less these days. But in 2018, 2019, gasless transactions was that was the thing that everybody thought we needed before we could have mass onboarding of users. I still think that this is important, and 7702 unlocks this. So that's kind of the motivation for 7702. 7702, the implementation went through many iterations, and what we've ended up coming up with was this a new transaction type that has a mechanism that allows EOAs to sign another message, an authorization message, and then that authorization message basically creates an in-protocol proxy for the EOA account. And what that basically means is that whenever you call that EOA account after the 7702 transaction has been processed, then the code that they have delegated to will execute rather than no operation executing. So this is going to allow a lot of new functionality for EOAs, but a lot of new security concerns, things that weren't really possible before. So this is a really good thing to be thinking about if you're looking at the Pectra scope for potential issues. And then the last one is just a pretty simple EIP to allow execution layer clients to better support different blob counts. Obviously, like we increased the blob count in Pectra to 6 target, 9 maximum. But the way that most execution clients in particular have handled these types of changes is they've been static variables within the client binary. So if you wanted to try and test a network that had 24 blob count and 12 target, then you would have to change the source code and recompile. And this isn't great if you're wanting to run a lot of experiments and you want to see how clients behave in these different very high blob load environments. So, we kind of killed 2 birds with 1 stone. We implemented the increase for Pectra from 3.6 to 6.9, and we also gave the testing and the DevOps teams the ability to now spin up test nets that have much larger blob counts. So we can start getting data about where should the blob count go in the future for Fusaka and for what comes after Fusaka. So this is just a pretty simple change to the client configuration file. If you start your client up with a Genesis JSON, you have your configuration of forks and everything, just a new field in that file. Cool. I think that's all the execution layer EIPs. Terrence, do you want to come talk about the very few consensus layer EIPs?
All right, thanks, Matt. That was very nice. So I will go over the consensus layer EIPs. 1 second. Okay, so something I do want to mention is that Matt did a very good job on covering, for example, there are cross-layer EIPs between EL and CL. For example, EIP 6110 and EIP 7002. And the consolidation, they are very good examples of something that is consumed in the EL through some system contract, but that message is passed to the CL. So when you want to propose a block, you will get those requests from the EL and you pack those into your block. And then every node will process those blocks and verify the object. And what is very important here is that because of the gas is already paid in the EL, if the CL sees those objects as invalid, the CL will not fail the block. I think for people that are auditing, this is a very cool, very good area to find bugs, because if any CL that mark those blocks as invalid, you will get a state transition failure. You will get a disagreement between, say, Lighthouse and Prism, and you will probably win some bounty there. So I think that's a good area to find bugs. I guess one thing that Matt didn't cover that I will have to cover is this EIP 7251 more in depth. Is that today as a staker, you deposit 32 ETH, right? And 32 ETH means you have 1 validator. But if today, say, you keep accumulating balances because you're doing things right, you get to 33 ETH. But the extra 1 ETH, you're not actually gaining anything for that 1 ETH. Your yield is based on 32 ETH. So what people typically do is that people will typically do this withdraw sweep. So every week you get this sweep back to your depositing address, right? But now the question is that how do I keep consolidate I have to keep waiting until another 32 ETH to deposit another validator, and that's not ideal. So increasing max effective balance allows you to have this max effective balance from 32 ETH to 2048 ETH, meaning that you don't necessarily will have to withdraw when you're about 32 ETH. You can keep earning interest up until 2048 ETH, and that's just still under one validator. And that's very nice from protocol's point of view, because now you're just sending one message, but you have multiple keys, and it allows like future extension, like single stop finality, because currently the bottleneck is that we have so many messages per slot, and network just doesn't scale unless we have some very nice aggregation scheme. So that's EIP 7251. Let's EIP 7549. It's pretty interesting. It's basically, so currently attestation is based on beacon committee. So you have your total active validators. They're about 1.1 mil right now. So you divide that by 32. That's how many slots per epoch. You divide that by 128. That's how many validators are in a committee. And then you get that many committees per slot per epoch, right? But then, so every validators will essentially sign a message based on being that committee. And that gets aggregated within a committee. So you have aggregate message, right? But you can think of, we can be even more efficient, that we can actually have this two-dimensional attestation where that for every slot, we just aggregate them in a way that, so you have your aggregation per committee, and then you have your committees bits basically. So as a proposer, instead of having to include 1028 attestations for all the committees, I could just include say up to 8, because they are all voting for the same thing anyway. The only thing difference is what committee they are, and that can be represented through a bit fields basically. And this is the, so this is the send attestation message. I guess if you want to look for bugs in this area, you could like, for example, look at whether like the block that the proposer proposed are packing attestations sufficiently, whether there are like attestations they're not packing, whether there are attestations that's packed in the previous block. So you want to avoid basically like not efficient block attestation packing. Let's see what else are there. I can, blob throughput increase, EIP 7691. So this is another like cross-layer EIP. So EL supports that, because now as a proposer, when I want to build a block with blobs, I get those blob sidecars from the EL. So now the EL will essentially increase from 3.6 to 6.9. So I can get up to 9 blob sidecars from the EL, and I will propose that. So from the CL side, the changes are I will essentially just broadcast more blob sidecars. So instead of 6, I will sign up to 9. So you should see more blob sidecars through the gossip subnet. So making sure that the clients subscribe to blob sidecar subnets from the 3 ETHDenver blob sidecars is important, to make sure that CL clients actually storing the ETHDenver blobs up to 18 days. That's also important. And making sure the CL client just basically aware of can be 3 ETHDenver blob sidecars in a slot. That's important. The general purpose execution request. So this is the one, as Matt mentioned, that there's an engine API between the CL and the EL. So this just adds a new field for execution layer requests, so we can get them and process them, including in the block more efficiently. There's not much to do there, I think, in terms of like finding bugs. So yeah, so I would think like the source of bugs on the CL side, you will see mostly are execution requests, making sure that as a CL, I process those requests. If the requests are invalid, I don't mark the block as bad, and that's really bad. So I kind of will continue, but I will log some messages basically claiming the execution request is bad. Then another one is just making sure that the CL can process and propose up to 3 more blob sidecars per slot. And then the third one is the attestation, just to make sure that the attestations in the block are packed efficiently. There's no wasted space. And this also implies when we do some sort of slashing, the slashing are also using the new attestation format. So making sure the slashing works, and then the slashing protection works as well. So yeah, that's from the CL side. I'm sure we'll cover more in the afternoon session. But yeah, I'm here all day. Feel free to ask us any questions. Thank you.
Used to be so insecure, always drowning in the storm. The sky was falling, but you held up the air. Now I'm feeling you everywhere. Sirens are screaming, I just can't relax. Currents are strong and you're pulling me back. Oh, 'cause when I fall and hit the wall, the only escape is your voice in the rain. And that's when you whisper. And that's when you whisper. And that's when you whisper.
Long hair across the room, baby, she got that glow. I know you see me over here, so dance on me real slow. We've been going for about 2 hours, and I don't even know your name. So baby, please reveal. Your friends are calling you, baby, stay with me instead. I know you're saying that you're tired, there's a door that's in your left. Even if I go, I still think of you in my bed. Oh, it's a good time, good time, good time we had. Scent of your perfume has got me lost in the haze. And all this moment depends on the records that the DJ plays. Baby, move a little bit closer, 'cause I wanna feel you, baby. I wanna feel you, baby. Your friends are calling you, baby, stay with me instead. I know you're saying that you're tired, there's a door that's in your left. Even if I go, I still think of you in my bed. good time we had.
Yeah, that sounds good.
I know it's hard to admit it.
hearts may go. These strangers know all the words at my shows. I tell, she loving our style. Shit makes her face red whenever I smile. I lay down, takes off her clothes. Wake up, I leave for the door. Tell myself I don't need a drink. I got champagne iced in the
All right, hey guys. Hope you had a great lunch break. We're gonna get started again and jump straight into the EIP walkthroughs. Looking at the code, looking at the specs, do a really deep dive in all of the Pectra EIPs. So starting us off, we're just gonna go in numeric order with the EIPs that were included in Pectra. So Gary from Besu will start us off and show us about EIP 2537, the BLS precompile.
Hey, how you doing? Oh, good old BLS. Interesting thing about 2537, it was basically done and ready to include in the London hard fork in 2021 and was kind of ripped out at the last moment. So this is kind of an oldie but a goodie. What's interesting is that at least in the Besu client, we had an implementation that did date from 2021. So when we went to implement this for Pectra, we had something to start from, but there were significant changes over the course of implementing it. Namely, we removed the multiplication code. So just kind of little history here first. All the gas costs were changed. And then we added some subgroup checks for safety. So if you're kind of looking for avenues to kind of poke around corners, I'd be looking at all of the changes that happened between 2021 and today. So just kind of running through it quickly. We have, let's see, what is it now after removing mul? 1, 2, 3, 4, 5, 6, 7, 8, 2, 6, 9 precompiles. So BLS 12 G1 add, it's just a precompile where you have G1 inputs, G1 encoded inputs. They're 64 byte packed, and it's functionally you're just adding 2 G1 points and getting a result back. G1 MSM is multi-scalar multiplication. So you provide a G1 point and a constant, and the result is the result of multiplying those two together. G2 add, same kind of thing, but a G2 point. G2 MSM, same kind of thing. Pairing check is interesting because you're doing pairing checks between individual points. And this actually had a defect that was discovered yesterday. So this is kind of hot in that there's a pairing consensus issue currently on Holsky because that's the only network that has implemented this PR. So you're not going to get any credit for finding a consensus error there. If you go to the Ethereum Magicians thread, you can find the BLS 12 381 pairing consensus issue right up from Marius. So as I said, you can run through the EIP. Largely, it's those precompiles with a specific gas cost per operation and per input size. In Besu, we implement all of our really heavy cryptographic operations in kind of a native sidecar library called Besu Native. If you want to do a quick walkthrough there, Besu, like Geth, is using the NARC library to do the heavy lifting for BLS. So if you go into Besu Native and look at the NARC implementation, we've got all of our precompiles, contract tests, and what's really handy is all of the use cases, all the test cases in here. The format here is that you get an input input point, an expected output point, and an expected gas cost. So that's used for pretty much all of the different precompiles. It's a good way to kind of bootstrap some test cases. In the NARC implementation in Besu, we have some convenience mechanism that will allow you to generate points. If you want to just, looking for it right now, since it's off the top of my head, where is that? Oh, come see me after if you want to find code to help you generate points. Some interesting errors, boundary conditions, subgroup checks were added. You need to make sure that all of the points fit in the field modulus. You need to make sure that they're on the curve. You need to make sure that treatment of the infinity point is consistent throughout everything. I think that that's, if you wanted to attack those precompiles across different clients, that's what I'd be looking at. The subgroup checks, the gas cost changes, and anything for the infinity point. And I think that pretty much covers it for 2537.
This isn't goodbye. Come on, just close your eyes. We'll test our faith like rolling dice. Like rolling
Hey everybody, I'm Justin. I'm on the Besu team. I work with Gary. I'm going to talk to you about these two EIPs here. We'll start with 2935. Pectra adds the ability for contracts to get the hashes of recent blocks. So the key update has been to the way that the block hash opcode works. Instead of it being kind of implemented natively, it is actually implemented by a separate system contract that has a ring buffer in it about 8K. So I think the EIP is pretty straightforward. If we look at the implementation here, this is a link to the PR, and I've filtered it down to the interesting bits. And so for instance, the way that this is implemented in Besu is we've introduced a new delegate for resolving the block hash opcode. In the past, it was kind of implemented in Besu itself, and this is now going to delegate to the known system contract and look it up there and package it. So this prog block hash processor class is kind of what does the real meat of the EIP. There are accompanying tests, obviously. So if you want to, use that to drive it, I think that's probably a good place to start. If we look at the implementation here, I think the meat of it is actually right here in this process block hash method. And you'll see that it does have some dependence on, the world state. It needs to be able to get a handle of that. Needs to be able to store the current hash when it got a new block, etc. So yeah, that one's actually pretty easy. It is summarized in that class there. Right, and then I can also talk a little bit about increasing the call data cost. So this is going to be a major impact on gas pricing, right? Gas pricing is one of the things that we have to be super careful about when we change opcodes and we are trying to align on state. How much something costs is often a thing that we get hung up on. So this changes anything that costs kind of over a floor amount is going to have a new price after Pectra than it did before. And you can see the formula here. All right. And in Besu, where that is relevant is in Mainnet transaction processor. This is a very critical class. How many people here are Java fluent? Rad. Okay. All right. You'll probably see this in the other clients as well. There's going to be a step where you need to calculate the intrinsic gas of a transaction. This is what we can know about the transaction before running it. So there will be some things that you can deduct immediately right off the rip on your gas bill. That has changed. So take a look at that. That's a good thing to take a look at. Transaction validation, similar approach, right? Like you need to figure out the intrinsic gas cost and make sure that it's even going to be valid without executing it. There's accompanying tests. Those are always a good thing to copy and hack on. And this prog gas calculator is how it's actually presented to Besu. So this is a protocol schedule aware gas calculator. So as the protocol schedule sees the next block that it needs to switch to the next fork, we grab a different gas calculator for that instance of the EVM that we're going to be executing. So this is where a lot of the implementations are. It also has a corresponding test, so go nuts. Yeah. So I think that's it. What's next? General purpose execution layer request. Matt, you want this?
So much on my mind. Praying I'll be fine. Pray I stay alive. Want this shit for life. I want this for life. We gon' be alright. We gon' be just fine. I like this. Lose my mind to this.
Okay, hello again, guys. Woo. All right. I'm going to give you guys an overview of 7685. So like we mentioned earlier this morning, 7685 is sort of this EIP that's supposed to take a bunch of different request types and put them into a single package that's easier for execution clients to reason about. And it's kind of gone through a lot of iterations, but at this point, what is actually happening with 7685 is that we are taking in all of the requests that have been created during the block via deposits to the deposit contract, via exits and withdrawals from the 7002 contract, and consolidation requests on the consolidations contract. So those get, each individual type gets combined into this object request data, and then we prepend the request data with the request type, and each of these, each 6110, 7002, 7251, they all have their own request types. So that helps us differentiate them when we're decoding them and we're verifying that the block was executed correctly. So that gets added into the header. There's a handful of edge cases in this. I think one important thing to note is that with the requests, we wanted to create a hash that was stable. And what I mean by stable is we wanted that hash to be stable across forks. And originally when this was proposed, if you didn't have any requests for the type, then you would hash just the request type into the overall request hash. And that created a problem because if in a new fork we added a new type of request, then we would change the Genesis hash. The Genesis hash would now kind of depend on what types of requests you have. And so we added this edge case within this compute request hash function that says if the length of the request of this type is less than is less than 1, so it basically 0, then we do not put it into the hash digest. So this kind of gives us this ability in the Genesis hash to sort of know that, no matter which fork configuration you get, like given this header, this is going to be what the hash is. And I don't know. I mean, for Geth, this was kind of an important thing. I don't know if you guys really cared that much about this specific property, but we ended up changing it, the AP a little bit to support that. Okay, so what does this look like in a consensus client? Let's go look at Geth really quickly. Seems okay. Can't really see the comments super well. So if I go into our types, if I go into our types and I look at our header object, this is where we're going to add the requests, this new request object. So as you can kind of see, there's the core of the header, the things that have sort of been around for a very long time, pretty much since Genesis. And then now you start seeing the stuff that we're slowly adding in. So we added the base fee in with 1559. And then we added the withdrawals hash with 4895, and 4844 added even more stuff. This blob gas things 47. The header continues to grow, and the final element, for now, is the 7685 requests hash. So before we had the request hash, before we implemented this, we had 3 more elements. We kind of had like the 6110 deposits hash. We had the 7002 exits hash, and we had the 7251 consolidations. So originally in the header object, we had a hash for each of these different request types. And what we decided to do instead is combine them into the request hash. And this makes us a bit more future compatible. As we add more requests, we don't need to keep adding new things to the header. So this is a really nice property. I don't know if we still have this in the body. No, not anymore. So we also used to have this in the body. So also every time we would add a new request, we would have to add that request to the body. With 7685, we kind of realized that you don't really need this stuff in the body. They're not input into the state transition function. They're actually output of the state transition function. And just like receipts are something that's sort of like separate of the body. You generate the receipts by executing the block. And so we kind of realized same type of thing with these requests. The requests are defined in the transactions. And so we can actually generate them just by executing. Okay, so that's the request hash in the header. The probably couple most important places where these show up, if we go to the Geth state transition. State processor, sorry. If we go to the Geth state processor, we can see the requests. So basically here in the state processor, we have this loop. And this loop is just going through all of the transactions in the block, and it's executing those transactions. And then it is accumulating the receipts for all of those transactions. So basically, we've processed the block. The block has executed all the transactions. We're on to the next step. And so usually when you think about the state transition function, you kind of just think about, we just executed the transactions. That's the state transition function. With Pectra, there is now kind of a new stage that happens after the state transition function. So you can sort of see, if this block number and block time is a prog block, we have more work. We're not quite finished. We have to deal with all of these system contracts. So here you can see we start accumulating those requests. So we run these several functions. We run the 6110, parse the deposit logs. That's just, like Justin said, you're just going through all of the receipts and you're figuring out which of the logs had to do with the deposit contract, and then we put them into that request accumulator. Same thing with 7002, same thing with 7251. So we're building up that that slice of requests, and when we have finally accumulated all of them, we can return it as part of the result of the total result of executing that block. And then once we have the result of that block, I think it's, where is it? Process result. We want to access the requests. I think it might be in a different file here. Validate, block validator. Yeah. Okay. So then we have, after we have processed the block, we have some sort of stateful validation. Like we need to validate the receipts against what we received over the network. And we need to validate, now we need to validate the request. So if we come into here, we're doing this validate body function. Let me pull it up so you can see it. So we're doing this validate body function. We're giving it the block. And we've, at this point, kind of filled the block in with the generated stuff, the receipts, and the requests. No, I'm sorry, it should be validate state. So we need to do validate state. Validate state is where we pass in our result, our process result, and that's where we do the validation of the receipts, and that's where we do the validation of the requests. So you can kind of see here, make sure the Bloom filters match, derive the hash of the receipts, make sure that matches what we expected, and then here's our request. So if the header has requests, that means it's a Pectra header, and so we need to calculate the hash for the requests, and we need to make sure that all of those are matching. So that's kind of the complete look at 7685 and the consensus on the consensus side within the execution layer, but there is a lot of glue code with these types of like EL, CL related changes. So not only do we have this in part of our state transition function, but we also have in our engine API, which in Get is called Catalyst, we have a lot of stuff about the requests. So as part of new payload, you would be receiving requests from the consensus layer, and you would need to then, validate these requests. And the validate request is a pretty pure, it's just basically a pure function. We're just trying to do some really simple verification. Are the requests ordered the way that we expected them to order? Are there requests that are empty? Just things that we can know without executing the block. So we can, do this very high level verification. And then as we're executing the block, we're executing the state transition function, which will do the full verification of those requests. I think that is pretty much the only places. Yeah, that's pretty much the only places we have 7685 in the code base. Let's jump up to the next EIP. Okay, perfect. So I'm gonna do 7702. Yeah, I have some slides for 7702 as well. Okay, let me not share my screen so I can pull up my personal Google Drive. Don't want to leak any information. Let's see. Sorry, the internet is being just a little slow for me. There's a lot on 7702 for security auditors to look at. It's a really interesting EIP. Has a lot of implications. Okay, let me share my screen again. Nice. Okay. So I presented a lot of this stuff at DevCon. If you want to see the talk in full, feel free to just search for 7702 DevCon Bangkok, and my talk will come up. But I'll go through this pretty quickly just so that you have a visual idea of what 7702 is. Then we'll kind of look at the implementation, Geth. So there's a lot of really fun Easter eggs about 7702 and how we got here. Vitalik originally wrote the original proposal for the EIP in 22 minutes because, it's Vitalik. The EIP has changed a lot since he wrote it in 22 minutes, so it wasn't the end all be all. But yeah, So 7702 has been in the works for a pretty long time. Before that, we were involved with 3074. 3074 was actually what was accepted into Pectra about 1 year ago, February last year. And in May or so, people started realizing that they wanted something slightly different than 3074. They still wanted to make EOAs better, but they needed the shape of it to change a bit, and that's kind of where 7702 came in. So you can kind of think of 7702 as this Trojan horse that sort of still like brings the 3074 functionality in. And yeah, this is 7702. So it gives you batching, sponsorship, privilege de-escalation. Most importantly, in my opinion, is bootstrapping. Like, we already had all of these things with smart contract wallets, but people weren't really using them. And if they were using them, it wasn't really giving the experience that people wanted. So 7702, a big piece of the motivation is to make it so that everybody gets to take advantage of those like top 3 things. You know, all of the wallets get to use it. All of the dApps get to expect that its users will have those things. And, you know, as security auditors, that kind of means that there's going to be a ton of different places that 7702 is going to be relevant in your work. It's going to be relevant for you when you're auditing application smart contracts. It's going to be relevant if you're auditing wallet software. It's going to be relevant for you auditing clients. So it's, you know, a pretty full stack change to the Ethereum protocol. Okay, so how does 7702 work? You have this account today. This is what an account looks like on the Ethereum execution layer. And what we're trying to do is we're trying to make the code in there have a smart contract wallet. How can we do this? 7702 introduces a new transaction type called the set code transaction type. It looks pretty much like a 1559 transaction, except it has a new list in it called authorization list. And inside that authorization list is the exciting stuff. This is where you get to delegate to an address that will execute that, you know, the address of code which you will execute when your account is called. So you have a chain ID. You know, all this stuff is like pretty similar stuff from your transaction. The address is a different type of contract creation than what you might be used to. You might be used to calling the create opcode or sending a transaction that has a nil address, and then you run the init code, and that init code puts some code into memory, and then you return it, and then that's the contract that gets deployed. 7702 was like, we're going to do this totally differently because why not? And so we have a concept called creation by template. So instead of running an init code, let's just directly write that template into the account, and we'll later initialize it via a regular call. No need to have, you know, more special call frames that have to be tested at every future hard fork. Just use the same facilities that already exist in the protocol. Why do we do this? It's a bit less call data. Instead of needing to pass the, you know, wrapper bytecode that sort of creates the same functionality, we just give a 20-byte address and it directly writes that code into the account. We also think that this is going to minimize the odds of people change their delegations a lot. I guess we'll see what the reality holds for us, but a big part of 7702 was to try and get people to not change their delegations a lot and to, you know, stick with a specific wallet. They can and should still be able to change wallets if they need to, but we don't want people to just be sending a bunch of one-off delegations for a transaction batch that they're submitting. Okay, and then yeah, 3607 has this very specific aspect of it that says that transactions cannot be originated from accounts that have code. Obviously, if your account is going to have code and we want you to still use your EOA, we have to add a little bit of a caveat to that and say that if you're a 7702 account, it's okay. You can still originate transactions. So that's all part of 7702. What is actually getting written into your 7702 account? So what is getting written is a delegation designator. This is a really long, you know, byte string that gets written into the code portion of your account, and we'll break down what each of these pieces are. So the first byte is this EIP 3541 designator with 3541, which when did this go live? Was this Shanghai? I think this is Shanghai. Basically, we knew that EOF was probably going to come at some point in the future, and we needed to make this domain space where EOF could get deployed. But we found that, hey, you know, this is a very nice mechanism within the protocol now that we can have special contracts that no one else can deploy. So this EF lets us do some of these 7702 behaviors that wouldn't have been possible without it. So this basically is saying that this is not a user contract. This is something that was placed here by the system, and so we can interpret it as if we're the system. The next bit is the 7702 prefix. I think EOF is the prefix 00, so 7702 is just creating a different discriminator that says 0100. And then you have the target address. So does anyone know what address this is, by the way? No. This is from the Ethereum test repo. So I think this is like if you look at all of the like Ethereum /tests, they all come from this A94 account. It's I don't know, if you just Google this account, the private key is everywhere. No, I think like even the before Ethereum /tests, the OG, the JSON tests. Yeah. Okay, so anyway, so the target address, this is the address that you want to execute within your account. And that is like obviously the payload that you care about. You just have to have all this like prefix to make it work. So that's the delegation designator. Boom. And then you have your signature. Bang. Okay, so this is the implementation. We're actually going to look at it in guess, so we don't have to look through this. And yeah, we don't really need to go through the example too much. Just know that you can put you can delegate your account. I guess we can talk about the gas cost really quickly. So the intrinsic cost is extended to charge 25,000 gas per authorization. And the reason that we do this is because 25,000 gas is the cost to create a new account in the EVM typically. And in the worst case with 7702, we're going to be setting code for an account that doesn't exist. And so we're just ahead of time charging them for the worst case. And as we're executing this, we'll possibly determine that actually there is already an account there and it's not the worst case. And so we'll just refund them at that point. The refund mechanism uses the same refund mechanism that you might be used to in the EVM. So it's capped by this 20% of total gas used. So it's not going to be a one-to-one refund perfectly, but in general, it's, you're going to get refunded and it's going to be somewhat close to what the expected cost is. Yeah. Okay. Prague, early 2025 or mid 2025, Cool. Okay, let's look at the implementation of this in Geth. So in Geth, we have a set code transaction. This is where we have defined most of the stuff related to 7702. So there's our trusty old prefix, EF0100. We have our set code transaction structure. And this set code transaction structure, again, mostly like 1559 with the addition of the auth list. The auth list is defined here, chain ID, address, non-signature. All of these are kind of the expected thing. Most of this stuff is pretty boring. Not much more to say about that. But if we go to our state transition file, we can see how we're actually processing this. So the entry point for our state transition, sorry, it's hard when the font is so big. The entry point for our transition is this function execute, as one might expect. So execute is the thing that we basically call on the block to start kicking off all of the verification of the block header, the transaction, all of this stuff. Or sorry, this is what's called on the transaction to kick off all the transaction verification. So we're kind of looking at a transaction level. So the first part of this here is all really focused on, is the transaction paying enough gas? Does the account have the money to pay the gas? If it's Prague, you can see there's that the gas cost, the call data gas cost increase. We have to calculate what is this floor data gas cost. That's a new change. So all of this stuff gets processed. We're getting the database ready. If it's a contract creation, we might do something different. And then here, right before I think we make the call. Yeah, so down here we would like start executing the EVM for the transaction. Right before that, we start looking at these authorizations. So if the transaction's authorizations is not nil, That means that we have a 7702 transaction in front of us, then we need to go through the authorizations that exist. So this is a list of all of the authorizations in the transaction, and we will just apply each of them directly. So how does this work? First, we look at the authorization and we have to validate that it's even, a valid, reasonable authorization. And there are some cases where the authorization might not be valid at all. For instance, if the chain ID does not match the current chain's chain ID, not a valid authorization. We cannot accept this under the chain. If the authorization nonces, I guess I should say these the errors here don't cause the transaction to be invalid. They cause the authorization to not be valid. So the transaction will still pay for an invalid authorization. It will simply not process the authorization. So we're validating if we should process this authorization. So we've checked the chain ID, we've checked the nonce, we do the authority recovery. It's possible that the signature might not, recover properly, in which case that would not get processed. And then we have to deal with the hot and cold of the accounts. Got to have that set correctly. And if all of that's good, and if we can parse the delegation okay, then we can just say that this authorization is going to be valid. And now it's time to start making the update. So for the update, we check to see if that account exists in the state. And then if it does, we add the refund, like mentioned before. They paid for the worst case, need to refund them if it's actually not the worst case. And then we will set the nonce, doing the nonce bump so that the authorization can't be replayed again later. And finally, we set the code. And so we set the code to the, I guess, okay, there's two cases. So we set the code to the address that they've delegated to, but there's a special case that we've added so that you can make your account look as if it has never delegated to any account before. If you delegate to the 0 address, then we will not write to the 0 address using the delegation designator. We'll actually write the nil code value. So your account will look like it's an EOA as if it has never used 7702 before. So that was a nice aspect of it. So this is the consensus implementation of 7702. Let's quickly look at the transaction pool. If you are an auditor looking for bugs for Pectra, I would probably look at the transaction pool because it is the least tested aspect of 7702 right now. Where is it? Okay, I want to go to the legacy pool. So in Geth, we have this kind of abstraction of different types of pools. We have the blob pool and we have our legacy pool. So the legacy pool is the implementation of all of the transactions other than blob transactions. And it has some interesting trackers in here. Most importantly, we have this all lookup object. And the all lookup object is basically a map of all transaction hashes to the actual transaction object. And we've extended that to also track authorizations. So kind of what we were wanting to do, we have a few, there's a few different properties that we're trying to retain in our transaction pool, a few things that we don't want to allow our transaction pool to do with respect to 7702. And you can kind of see a handful of them written out pretty explicitly in this legacy pool test. So if I go to test set code, there's a pretty long list, and I can just mention a handful of these. So one is we only want to have one in-flight transaction for accounts with a delegation set. In general, we have this property with 7702 that we've inherited from other account abstraction proposals like 4337, where because one, the account can now do batch transactions, there's much less reason for them to have a bunch of transactions pending. If they want to do a bunch of operations, they should just batch them into one transaction. So there's less value in that. But also there is risk in allowing them to have a bunch of pending transactions. Because historically, if you have a transaction from an account, we can kind of determine statically if all of the pending transactions for that account will be valid by simply looking at the cost of each transaction and the balance of the account. And because the account's balance cannot be changed by any external account, it can only be changed via an originating transaction from that account, we had a pretty good expectation that the transactions that we have in our pool are going to go on chain and they're going to pay. With 7702 and with, account abstraction, smart contract wallets in general, you don't have that property. Anyone can call the smart contract wallet from any transaction, from any origin, and they could possibly spend all of the balance of that account. So for this reason, we don't want to give people the ability to just create a bunch of stacked pending transactions and then invalidate them all in a single transaction, in a single call. So we have decided that we want to sort of keep this one pending transaction in flight requirement, and we have a bunch of tests to do that. So here we're making sure that if a account who has already delegated using 7702 has a pending transaction, that they will not be able to submit more transactions to their account with future nonces. All they can do is that they can replace their transaction that is currently pending with another transaction with the same nonce. So that's one thing that we're trying to focus on. There's some more edge cases. We don't want to have accounts get deadlocked. So originally when we were implementing the transaction pool changes, we were very hard on senders, and we didn't see any reason that they would have a pending 7702 authorization and a pending transaction from their account. And so originally what we were thinking is that there should only be one. You should either have a pending transaction or you should be on another transaction as an authorization list message. And what we realized is that because authorization list messages aren't validated, this is an important property of 7702, we only validate the transaction sender. We're not going through every authorization message and validating each of those. That would be a lot of EC recovers. That would be a lot of state lookups. So because we're not validating that, people can go into the history and just grab a historical authorization and then put it in a transaction that doesn't pay very high, and then it sits in the pending pool, and that would kind of cause this liveness lock for that user because they can't invalidate it. They can't invalidate that transaction because they didn't send it, but they also can't originate a new transaction because their account has a pending authorization. So we've sort of relaxed this. No. We should do that at some point. Maybe some of the auditors online would love to build this. I'm sure you could probably win some awards doing this. Yeah, so we've ended up relaxing these requirements a bit, and we're basically allowing one pending transaction and as many authorizations as the account wants to have, rather than making them choose a pending EOA transaction or a pending authorization. So this is in general kind of relax that requirement quite a bit. Let's see if there's any other ones that are important to talk about. Yeah, generally just want to make sure that we can that we can replace transactions, making sure that we're not leaving dangling tracking of the delegations. But yeah, that's mostly the transaction pool. So I guess at a high level, what you can think about is happening is that we're sort of creating this state machine that is tracking all of the accounts that have pending authorizations and all of the transactions, and using that information to determine should we allow this transaction into the pool or not, or how many transactions is the maximum number of transactions we should allow from this account right now, based on the state, based on the pending transactions. And so the lookup object is basically letting us do that. Okay, that's mostly 7702. Let's keep on going. I think there's one more amazing EL EIP, and then we can look at the amazing CL EIPs. Okay, 7840. I think I mostly described what this EIP was doing this morning, but just as a recap, the way that execution layer clients tended to make the configurations for the blob target and the blob max is that this was hard coded as a parameter within the client. Pectra is the first time that we've changed it. So we haven't had to have multiple versions of this parameter before. But in general, like we had the question about how do we test much larger amounts of blobs than on mainnet. And the problem with doing this before 7840 was that you would have to change the client implementation, adjust the configuration variables in the binaries, recompile it. And this didn't work very well if you wanted to have a big test net and test a bunch of different client configurations with different blob amounts. So that's a big reason that 7840 came to be. So 7840 specifically adds this new blob schedule dictionary into the config. And inside of that is a list of each of the network upgrades and what the parameters for the blob schedule should be. And so you can see that in Cancun, we had a target of 3 and a max of 6, which was introduced with 4844. And now in Pectra, we'll obviously have a target of 6 and the max of 9. And we've also been updating the base fee. We have the base fee update function changes. So this is just allowing us to at runtime kind of change those properties. So let's look at how we've implemented this in the client. That's going to be in parameters/config. So we have the blob schedule config here, and we have already started working on Osaka because we're looking towards the future of Ethereum, EOF, and then we have Verkle, also the future of Ethereum. And each of these have their own blob configurations. So the blob configuration is just, a pretty simple structure that is storing the target and the max. And we also have the default blob config. So we have the default blob config for the different networks that we're sort of keeping track of right now. So I can also show you why Haleski broke, if anyone was curious on the Go Ethereum. So we have these really nice default blob configuration set, and if you look at our mainnet, we have these really nice hard-coded chain configurations for all of the networks. And you can see on mainnet we have all of these nice forks and timestamps, and we have the blob schedule configuration, and we have this deposit contract address, really important contract on Ethereum. It happens to have all of the ether, most of the ether. And, we have it, we kind of have this for all the networks. And then Haleski, we have this, we have the same thing. It's, much newer network. And so many of the changes were started at 0. And you'll notice that we have our blob schedule config. We've scheduled Pectra. Pectra, went live on Haleski pretty recently, but you will notice that we were missing. I haven't pulled down the latest changes, but we were missing a very important element that you will see on the mainnet, which is the deposit contract address. And with 6110, because 6110 is actually going through the logs and looking at the logs to see if there is a receipt from the deposit contract, and then parsing that receipt and taking that and putting into the request hash, it didn't know which contract to be looking at. And so because we didn't define the deposit contract, it was looking for events that were emitted by the 0 address, which obviously there were no events being emitted by the 0 address. And so it was really as simple as basically copying the deposit contract address here and then updating with the correct value, which I think is just a whole bunch of 42s, something like this. I see. Which I think would put us on the same fork because neither of them would be creating events on Haleski. Yeah. Anyways. Right. Yeah. So we're still working. Terrence is still working on fixing that. And that's pretty much all of the EL EIPs for Pectra. I think I'm going to hand it over to Terrence now to walk through the changes in the consensus layer.
All right, hey, I am back. So yes, I got 9 minutes, so I'm gonna speed through this fairly quickly. So before earlier, we went through all the EIPs that's going to be in the CL. And then we summarized there are a few of them: EIP 6110, EIP 7002, EIP 7251, EIP 7549, and then the blob increase one. I guess like instead of like going to the code, I think the first thing I wanted to do is that like how CL does it slightly differently versus the EL is that we have like its comprehensive spec. It's the consensus spec. And then within the consensus spec, you can actually get like a fairly nice high overview already on what the changes are. So we have, say, this beacon chain spec, this fork.md, this P2P, and this validator spec. So I will go through the spec one by one. And based on the spec, which is a nice collection of Python code, you will be able to kind of know like what to look for already, like what is compliant. And one thing that's nice about this spec is that it generates some sort of executable Python spec code. You can also look at those spec code as well. And clients are all passing the spec code, so that is very nice. So here are the consensus like spec code basically for the Python. You can see it's very, very long just to show you how many things that we have implemented in Pectra. And the first thing you want to look at is this container section. So this basically shows you all the new objects that's coming in Pectra. Some of these objects are standalone. Some of these objects are encoded in the block. And you can see there's pending deposit, there's pending withdrawals, there's pending consolidations. And these are all based on the previous EIPs. And the requests we were talking about earlier are all defined here as well. And here are the single attestation, which is what I meant when we are changing the attestation type and stuff like that. And then you can see there's a modified container. So everything that's modified, meaning it's updated from before, because for every hard fork, something changed, right? Because we're breaking consensus rule. So in this big block body, you can see what is changed here are also commented, are also have a nice comment, basically. For example, like we said earlier, the beacon block body, we add execution requests. Therefore, this is new on Pectra. And then you can see there are previous objects that's also modified as well. For example, attestations, attested slashing, those are modified because of EIP 7549. Then we can wonder, well, what is EIP 7549? Then we can go back to the original EIP, then see, oh, this is the one that's moving committee index outside of attestation. So because of this attestation change, therefore this beacon block body change. So you can see there's like a cascade of changes from the bottom all the way to the top, right? And because of this object change, and like everything else also changed, right? So I don't want to scroll through, it's just very long to scroll through. But then you can see all like the helper functions for getting like the different things basically for supporting those changes. For example, like getting the attestation in the indices, getting the sync committee indices, the way you get a churn limit and stuff like that are also different as well. And us with the state transition function, everything's different there, right? Because of the new object, now you get a different state root. So there are typically two types of state transition function. The first is when you process the epoch, that's every 32 slot. And then the second is when you process the block, that's every 12 seconds. So those also changes as well. So as you go through this, typically you can reference that in the client code and just to essentially see whether they implement the spec accordingly, right? For example, this is process withdrawals. The client code should have the identical version of this process withdrawals, whether it's in Go, whether it's in ROS, the input should correlate to the output, and the output should basically match. So this is basically the beacon chain. And besides the beacon chain, there are also two other things that's important. The first is the P2P interface. And this is basically when we receive objects over P2P, the client has to decide whether whoever sending me this object is malicious or not, right? If it's malicious, then you have some sort of scoring function that you track with the peer. And then if the score is below certain threshold, you will disconnect with that peer. And then, so P2P defines like what is safe to import from the P2P's perspective. And for every hard fork, because of different object changes, that you will subscribe to a different subnet, right? So for here, you have beacon block, you have beacon aggregate and proof, and you have blob sidecars. And these are the new global topic that's changes from before. And then besides gossip, there's this RPC request and respond as well, because of like as client, as a node that you're syncing to the head of the chain, you will have to request that, whether it's by range, whether it's by root. And those are also different as well. So you have to study the client code and to see where they implement this and to see, whether there's something wrong with that, basically. And besides P2P, there is also the validator client. So these are typically in client implementation, it's a different type of software. So it's like more lightweight and they communicate with the beacon node through some HTTP interface. And here also changes as well. Now, when you construct the block, you have your block body. And then because of the object changes, because of different execution requests, this construction also changes as well. And so this is on the validator side. In terms of code, I guess I have 2 minutes. I can quickly show you that everything in Prism for the state transition function is under core Electra transition. So there's a core and is this Electra package, and everything within the state transition is under here. So yes, if you want to find bugs, and this is where you will find very juicy bugs. And with that, I have 2 minutes. So maybe we can move on to the Q&A or happy to answer any questions. Thank you.
You wouldn't like it up there.
started. Okay, are we good? Okay, hello everyone. My name is Hari, and today we have a panel with 3 core devs. And the goal of the panel is to represent the secure researchers and ask a lot of questions that they would be thinking about right now, just so that they can try to find serious bugs, if there are bugs in the Pectra upgrade. So let's start with some introductions. My name is Hari. I'm one of the founders of Cantina, and we're right now hosting this security competition along with Ethereum Foundation for the next Pectra upgrade. I used to work at the Ethereum Foundation. I used to build a Solidity compiler, so it's very close to me, this upgrade. So with that in mind, do you want to go next?
Hey guys, I've been with you all morning. I don't think I really introduced myself at all. Forgot about that when we started the introduction. I'm just so fired up about Pectra. It's not really about me, it's about everyone and all the clients. But my name is Matt. I'm on the Go Ethereum team. Been with the team for about 3 years, and before that I was at Consensus doing some research and development on ETH2 phase 2, and that led me down the path of contributing to the Go Ethereum project, and yeah, fallen quite down the rabbit hole.
Hi, I'm Terrence from Prism team. So I work on consensus layer client, one of the 6 consensus layer client, been with the team since the beginning. So I think we started it 2018, so about 7 years. Yep.
I'm Justin Florentine. I'm on the Base2 team. We get paid by Consensus. We are a Java-based execution client. I've been there for coming on 4 years. So I've been a core dev since about the London hard fork. Yeah, you'll find me online as Robocop's Gone Mad, in case you're wondering.
Nice. Okay, I want to get right away to the most important question that people are probably thinking right now. If there is a serious critical bug in one of the EIPs, one of the implementations in Pectra, what do you think it's going to be?
I think it's probably going to be on the client configurations.
What? Why would that spring to mind, Matt?
So I think one of the best ways to find bugs in core clients is to try and understand what our testing infrastructure is, and think about the things that don't have test coverage. I mean, there's a reason why people try to measure test coverage, because if you're not testing the functions, then you don't really know if it's working. And this is exactly what happened with Haleshki. We have a pretty solid testing infrastructure, and there are a lot of tests. But this was a very specific incident where we don't have a great ability to test that the baked in Haleshki flag on clients is loading the correct data. You know, all of our testing infrastructure is sort of based on custom Genesis files, custom chain configuration files. And so all of these things are tested very robustly. But the Haleshki, natively baked in information, beyond, some manual checks that didn't really exist before the testnet was forked, we didn't have the testing infrastructure running on that. So I would say, if you just extrapolate beyond that in general, I would guess that the biggest issues at Pectra are going to be around the things that we don't have super strong testing coverage for. And one thing that we mentioned when we were looking at the EAPs was that for 7702, the consensus aspects, the state transition aspects have pretty robust tests. So I'm not super worried about bugs necessarily in that, but the transaction pool, with the 7702 transitions have much less testing infrastructure around it. So that would be a place as a security person that I would be, pretty interested in looking into. So anywhere that you can find that there are changes around the protocol that don't have good testing infrastructure for is a place pretty ripe for bugs.
I probably will give an answer that people probably don't want to hear. I think the bug may exist at the MVP boost builder pipeline, where currently, I think this is still an issue today, where 95% of the blocks are produced through MVP boost relayer to the builder, but yet we don't have day zero comprehensive test for that. This is often something that's tested until the very last minute. And we have seen time and time again in Captcha, there was a withdrawal thing. We have liveness failure there. In ETHDenver, there was issues that builder was censoring blobs. Builder, like Flashbox, wasn't ready to build blobs, so they were building an empty block for block for a while as well. And that's probably something that, as a core developer, as a testing team, it's very hard to control, right? Because this is like external party that we don't often get to see relayer builders and stuff like that, and their readiness sometimes is questionable. I know they're trying their best to be ready for everything, but at the same time, it's just like it's very hard to do. And I think for Pectra, yeah, I think if there's one area of bugs that could occur, it could be there where I can give you an example. Maybe there's execution requests where they're supposed to include it, but one of the client did not marshal the execution request correctly and just default to local block. But in this case, it's probably okay. It's just you can always go back to local block building, but it's not nice. Yeah.
I think that covers it really what I was concerned with, honestly, like a lot of the things that Matt alluded to. One thing we haven't covered though, and one thing that is very hard for us to simulate too, is denial of service types attacks, right? Like pushing the clients past reasonable resources that the operators may have assigned them. That's a tough one. I don't have any good strategies for doing that other than we go through our code really aggressively. We hired a performance engineer who has been fantastic and has really helped us improve our performance tremendously. Like you may remember the merge that Besu was really struggling. Like Besu, there were some users that were reporting not being able to get timely attestations in. And we did a lot of work over the last 2 years to increase that performance. And so those are the things that caused us some sleepless nights, like right after the event. And we could not predict them because mainnet scale is mainnet scale, right? It's hard to simulate.
That's a great it's a great tip. Like, how do you think a DOS attack on one of the clients would look like? Like, how can a secure researcher try to find such a bug?
Well, I think the mempool is always a good vector for that. I would say the mempool and the P2P layer too, like Eclipse attacks, knocking people off the network so they can't find peers. Part of the way that Haleski manifested itself was through the peer-to-peer layer. Once we had, started going down the wrong chain, the clients that were on the right chain were rejecting the people that were trying to get repaired. So that was a pretty big bummer. The transaction pool, we had a transaction pool issue that, it was a kind of a denial of the service attack where you could flood the transaction pool with a nonce too far in the future and it would just hang out, right? And we had to build a whole new implementation of the transaction pool to address that and work around that. So I guess, networking and the dark forest would be denial of service vectors.
Do you want to?
I think in Pectra specifically, if you're looking for denial of service vectors, I think new cryptographic loads are certainly in there. 7702 brings in a lot of EC recover that some clients may or may not handle well. The BLS precompiles, every client is, not every client, but many clients are using different libraries with different levels of performance. I think that that's certainly a vector, is the cryptographic load in Pectra.
That's also like a, sorry, that's also like a great tip, because as someone inside the EF in the past, I would definitely say that a lot of the core dev specialty is not cryptography. So there are definitely, like, if you look at a historical example, like there was a bug in ModX. There has been cryptographic bugs in the past in clients. And if you are a secure researcher trying to find bugs in clients, I would definitely recommend looking at some of the BLS precompiles that's getting added to Pectra. The next question I have for everyone is, what would you say is your favorite upgrade in Pectra?
I feel like such a broken record. I love 7702. Such a cool EIP. So many ways to lose money. So many ways to improve the user experience. But I've been working on 7702 and its precursors for like 4 years. So of course I'm ecstatic to see it live finally on mainnet.
Do you have a second favorite?
Ooh, a second favorite EIP. No. No. I mean, I also got to write a lot of the system assembly contracts. So every time they say system contract, I get really excited because I get to write assembly for like a month and not have to do any real work. Just stick my head into the sand. Opcode after opcode. I can't believe people are out here writing Solidity. Like, it's so much easier when you just write each opcode. You don't have to think about anything. You just know exactly what's going
it's
to
a lot of fun
happen.
to peer review too.
So Felix was really unhappy that I was using a Rust project. He keeps saying that he's going to fire me if I use another Rust project. So he he decided he would write a new assembler in Go, and it's called Geese, the good Ethereum assembler. So yeah, all of the smart contracts in Ethereum are written with Geese.
Okay. I feel like that's worth looking into. If they just build their own assembler, maybe it's correct, but maybe there's a bug in there. You never know. So
I was just gonna say we have 2 audits on it. So there's literature out there, and I mean there could be some issues for sure, but definitely a good place to look at. There's not a lot of eyes on those contracts, to be honest. Yeah. I don't know. I assume most EL devs are just like, great, it's new address. We're just gonna execute whatever's at that address. But beyond me and Felix and Mikhail and some security firms that we hire to review it, it's not the most deeply reviewed stuff.
Terence, what about you? What about you?
I actually don't have a favorite EIP in Pectra. I don't like Pectra, to be honest with you. I want the PeerDAS. I want EPBS. I want Fossil. So I'm very looking forward to the next. I guess the thing close assemble you can say it's a PeerDAS is that one that will increase the blob target and max to 6.9. That it's kind of like useful for layer 2. So people that's consuming blobs because now it will be cheaper. So yeah, from that perspective, there could be bots fund there as well, because now it's like we need to heavily spend blobs to see if the network goes wrong, whether we see more reorgs. To also, we want to monitor like censorship. Say today, the builders may refuse to build blobs. If there's a high spike of MEV, they want to just propose a very juicy block instead. So there may be something to look for there.
I think PeerDAS, EPBS, and Fossil would be a sick hard fork. Just boom, there's Fusaka right there.
So I just heard that you don't like Pectra. So is there an upgrade in Pectra that you absolutely hate?
I didn't like the attestation one where you move the community index outside. I think that was like, this is honestly like our fault. Just like we say yes to it, everyone say yes to it. Just it's something that it looks so simple in the spec. It's a 2-line spec change that you add 1 line, you remove 1 line, but no one really like understood like how difficult that was to bring into the client code base, right? It's one of those things that it looks so simple, and then once you bring the client code base, you realize, oh, this is a 100-line change. Oh wait, there's another 100-line. Oh wait, there's a bug and stuff like that. So it becomes very difficult to deal with. And this is a very good lesson learned from all the client team members. It's just that we do not underestimate EIP complexity.
Justin, what about yourself? What's your favorite EIP?
So I do like 7702. Like I do like the just sheer mayhem that it's gonna unleash, and it's gonna be a little stressy. I'm not gonna lie. People are gonna do all kinds of wild stuff with it, and those are always the most fun things to me when you give a community a toolkit that they themselves don't know what they're going to do with, and they kind of have to sit and imagine for a while until they come up with something, because it's always going to be a surprise. I'm also looking forward to the blob increase just because I'm sick of hearing about blob increases. So like, let's get it out there and be done with it, frankly. I think there's two other legs of the blockchain scaling trilemma that need attention. And, scaling is, sure, that's very, very important. There's tons of people working on it, but the other two are, as important, if not more important, and they need their attention as well.
Yeah, my favorite EIP is probably 702 as well. I feel like it opens up like a much needed UX improvement in Ethereum, and like we've been talking about it for a very long time, and I'm finally happy to like see it in mainnet. So my next question is again about security. Can you explain a bug that you found while building Pectra, or something that was found in your client?
I mean, a lot of the stuff that we found was the stuff that we find every hard fork. It's, I don't think of any notable design gaps, the things that weren't defined or ambiguous, but gas costing, sometimes we miscalculate a piece of gas and we have to go back and trace through the EVM and correct that. But
I mean, we rely a lot on spec tests, for example, consensus spec tests, and this is what every clients do. I mean, we have unit tests, but it's not like comprehensive end-to-end, so we rely on spec tests. But even spec tests, they only cover the core transition function. Besides, there are also the P2P layer, and there are the validator client. Those two don't really have a spec test. So what it ends up is that we ended up finding those bugs on like Dora, like DevNet, for example. I can give you an example on DevNet 5. Prism was packing blocks that contain attestations, but those attestations are already included by the previous proposal. So we're just wasting space, keep adding attestations, even though that is included before. But that wasn't. You can't read. It's very, very hard to test that specific edge case, but it's very easy to see once you open a UI, you click a few things, you're like, oh wait, this looks wrong, right? So yeah, so that's probably the last time I found like something interesting.
I can say on 7702, some of the changes that were coming in late, we were really flipping back and forth on what data we should expose about the accounts code. So originally, we were thinking that if you would do Xcode size, Xcode hash, Xcode copy on the account, that you would get the prefixed 7702 information with the address, the full delegation designator. And then there were some proposals to change this behavior. So we decided to just return the prefix of the EF0100 value, and that was kind of riding for a while. And then I think maybe even in December, people were starting to say, actually it's important that we know what code is executing in the account, because if you're using some of these relayers, you want to make sure that relayer did relay your authorization message in the bundle, and you are only going to pay them if your account code changed. So we ended up swapping it back. So that was just like an example of, a pretty minute spec detail that received a lot of attention, and it took quite a bit of time to really settle on finally.
And the next question, I want to understand like what's after Pectra. I think Terrence spoke a bit about it.
What do you want
can't
after
wait.
Pectra? Yeah, what do you want in Fusaka?
Well, I used to work on Solidity, so I'm very, very biased towards EVM. I want more EVM changes. I want anything on EVM at this point. I will take anything. So I'm biased on like execution changes in the EVM. It doesn't matter if it's EF or not. Like I just want to see EVM moving forward.
I think like we're at this point in life that where you ask 5 different people, you will get 5 different answers on what they want, right? So for me, I think scale is the most important thing. So I want execution scaling, I want DA scaling. So that means that we want more blobs. So we need something like Pierre does to support that. If that's not enough, then we want something like PBS to pipeline the consensus, the execution, so you have more time to propagate the blobs. So that's one thing. I also want to increase the gas limit from 36 to something that's more reasonably safe, like 60, something like that. So this is what I want.
Why 60 and not 300?
I think there is state growth to me is the concern. I think unless we solve like statelessness or have some sort of state rent thing, and I think like we cannot push it to like the extreme. So I mean, again, I don't work on that very closely. Something to monitor, and yeah.
How about yourself?
I think, what I want in Fusaka, speed, right? So I think that's been the kind of meta conversation on the roadmap lately is like, how can we get Fusaka out sooner? What would it look like to get 2 hard forks out a year instead of 1? Not much can really fit in that right now. And right now it looks like, pure DOS and EOF are what's going to be in. I would love to squeeze in Fossil. I think it'll fit, but that's hard to say. That's asking a lot. I think I'm still holding out for Terrence's super based hard fork where it's all ePBS and Fossil and all that kind of stuff.
Maybe not for Fusaka, but I wish that it was more of a priority of core teams to be working towards proposals on Ethereum that fulfill the original philosophy of blockchains and Ethereum. If we look around today at how people interact with Ethereum, it's all through centralized providers and using custody solutions. At least, for the most part, people are storing their private keys, but there are a lot of people who completely are trusting third parties for information. And it doesn't really seem like we care a lot about this. So I would like to see us working more towards statelessness. I would like us to see us working more on light clients. I would like to see us adding more resilience to the protocol, making sure that transactions are included even in the world where most blocks are being built by 2 entities. So I get that kind of goes against the grain of accelerate, more blobs, more gas. I'm not saying we shouldn't do that types of stuff, but I think for quite a while, since proof of stake basically, we've put some of the core properties of the system on hold because we have to ship proof of stake, we have to ship the merge. And I think, if we're not going to make it possible for people to use these systems trustlessly, then what is the value prop of Ethereum versus Solana?
I have a controversial question next. So, Pectra is almost here, but people wanted to get Pectra out, much earlier. What do you think happened? What do you think could be done better next time to get Pectra out faster or the next hard fork?
On GitHub, there's a button. There's a code button, and then next to it, it's called pull requests. So if you want to see change on a repository, open source project, you can actually just press that button, and you can click new pull requests. And usually you have to have some code with it, but some of these are pretty simple stuff to implement.
We use it for specs too.
Type the title, description of what you've changed. I think a lot of the people who are getting Star Alliance Gold out there yapping across the world could probably open up their terminal and write a few lines on it.
Yeah, I gave a talk yesterday on kind of that, saying that, hey, look, all of these clients that people are building are very modular in different ways. You can submit plugins and you can build these types of things and then bring it to all core devs and say like, hey, I think we should do this. And oh, by the way, I made it work already. And it's a fast forward button on a technical debate, right? So it was much easier for us to not have to model things out and think about it. We can look at something concrete. So Ethereum is participatory. Get out there. You want to move faster? Cool. The only other lever that we have to pull is actually to do less, and give it to you faster. So without having more input into the system, more bandwidth coming into the system, you can't get blood out of a stone.
I think testing is by far the bottleneck in terms of where we are today. Like, I mean, like we get helps from outside. Sometimes people open like typos PR to get airdrop, but probably shouldn't be doing that. But yeah, I mean, I think more use for PR will be nice. I think, but to me, testing is by far the bottleneck right now. I think like if Panda Ops, Perry and team are doing such an amazing job on just like testing, finding bugs and fasting. I think one of the feedback I get is that we should have done, we should do that earlier in the cycle. Just like once the client's ready, just start DevNet already as early as possible so we can find bugs. So just like when you do fasting, like time matters how long you fast for. Just you're not gonna see the bugs until you fast slightly longer. So I think testing is the bottleneck, and we need more testing infra, people that can help test.
So no SFI without EELS tests or something, right?
I also want to mention, there's only like 185 core client contributors or, core protocol contributors. And even that number might sound big, but you have to realize that there's a lot of duplication of effort, which is a good property of Ethereum. Like, we do like client diversity. And I think that it brings a lot of diverse voices into technical discussions that might otherwise be dominated by one technical voice. But you have to realize that like the median team size of a client is like 10 people. So how fast can an elite team, a technical team of 10 people ship? I would say that shipping a hard fork a year without major mainnet bugs is like quite a testament of success. And if we want to move much faster than that, then we need to figure out how to like really scale these client teams, because just saying let's ship faster is not, these people can only do so much every day. Everyone has the same amount of hours. Some people are more productive in those hours, but everyone has the same amount of hours. And if you have 10 people, you just kind of have a limit on what you can do. So if we have a client team that's 50 people, they might be able to do a bit more.
How do we get there?
I mean, that's a good question. I don't know. I mean, I was kind of asking you guys earlier, like, how do we make bigger client teams? It feels like fundamentally we've kind of reached this tribe size of like 8 to 13 people, and we've just sort of topped out at that point. And I think a lot of Ethereum, like core Ethereum feelings, is that we don't want to have these corporate structures. We don't want to have a VP of engineering, this is the type of stuff that would make all of us probably want to quit having our jobs. But like, you gotta be real. If you look at like the scale at which some other companies are executing at, they don't get to that scale usually by just like fun vibes and miladies. Yeah. And
that's not fun. Like, that's a burden, frankly, right? Like, so in my career, I've gone back and forth between individual contributorship and management a number of times, right? It's a pendulum that goes back and forth. And right now I'm kind of swinging back towards more of a management thing, right? So I'm not, doing as much individual contributorship, but I'm coordinating, I'm organizing, I'm communicating, I'm influencing, I'm doing all that stuff. And that's not a job that anybody else wanted. Like, I took that job because everybody on the team was like, we need somebody to do this. And I was like, okay, well, I have experience doing this. I'll step into it, I'll do it. And I'm still having fun. So like, hey, everybody out there, it's still fun. It's not as fun as like being an individual contributor, but it's still fun. So like, if you have those skills, like, don't be afraid to like, step up a little bit and try to help people, get that team past that max tribe size.
Terrence, any thoughts?
No, I agree with what they said. Yeah, I think it's definitely we need to scale the protocol, but we also need to scale the human as well, like to have more contributors.
I think we're almost at time, so I will end with one last question. I know many securities are listening, either here or a lot through like Twitter and YouTube as well. What's your final thoughts to them? They're going to be spending a lot of weeks trying to find bugs in the Pectra upgrade and Ethereum protocol. Any final thoughts to them? What should they be looking out for? Any tips on like getting better at finding bugs in the core protocol? Any final thoughts?
Please use responsible disclosure. Please. Security at ethereum.org. If you need anything to remember, don't submit it on mainnet. Seems like a crazy thing to say, but you have to say it sometimes. Yeah, I mean, good luck, guys. Pectra is one of the biggest upgrades we've ever done. there's some bugs out there, almost guaranteed. I think I said it before, but yeah, take a look at where there is testing coverage and where there is not, and dig into the places that there's less testing coverage and less eyes.
Yeah, definitely. And so Petra is near towards mainnet, right? We haven't figured out mainnet yet, but it should be sometime in April, fingers crossed. So be careful when you disclose blocks and look through client logs. Definitely try running a node. If you haven't tried running a node before, you will find like something that's weird. Always ask the client team, like what does this log mean? Sometimes maybe there's something there we just don't know yet, right? And definitely you can run unit tests with coverage, and if there's like a single condition, like if else doesn't have a coverage for the else, then something may be off there. So definitely dig more into there.
I think you guys pretty much nailed it. The only thing I would add is maybe keep top open while you're doing this. See if there's any resource, curiosities that folks aren't seeing. But yeah, responsible disclosure, please.
Yeah, I think that's a wrap. I really thank like Matt, Terrence, and Justin for this conversation. I'm pretty sure a lot of secure researchers also like appreciate your inputs. It's going to save them a lot of time getting to understand the protocol better, and hopefully like find some bugs and make Ethereum like more secure at the end of the day. So thank you again.
How big is that bounty again?
It's $2 million.
What? What?
You can, if you find bugs, you can get a share of $2 million. And I've heard that there may be already serious bugs in there.
Thank you.
Thanks, everyone.